Welcome back to another explainer. Today, we're decoding one of the absolute most terrifying and honestly most misunderstood events in human history. We're doing a full autopsy of the Chernobyl disaster. We're going to strip away all the myths and look directly at the complex physics, the deeply flawed engineering, and the severe biological impact of history's worst nuclear accident. So let's just dive right in.
Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown. This is space like you've never seen it before.
Just to set the scene for a second, I want you to imagine this level of sheer physical force. Quote, the reactor cover, which weighed about 1,000 tons, launched into the air, sending most of the reactor components up to a kilometer up in the air. I mean, that is the terrifying scale of the explosion we're dealing with here. But how did we get there? How does a seemingly routine test at a power plant trigger a disaster of this unimaginable magnitude? Well, let's step back and investigate the scene of the crime.
Section 1. The flawed machine, the RBMK reactor design.
Okay, notice the stark contrast in engineering philosophies here. On the left, you've got standard US and global reactors. They feature this massive, thick concrete dome for containment, and crucially, water acts as both the coolant and the sole moderator. But look over at the right side, the Soviet RBMK reactor. Completely different. There was no containment dome whatsoever. It used pressurized coolant tubes, and instead of water, it used a solid graphite moderator. Now, why does that matter? Because in a standard reactor, if you lose your cooling water, you also lose your moderator, right? The nuclear reaction just safely stops. But in the RBMK, that solid graphite moderator stayed right there in the core, meaning even if all your cooling water boiled away, the nuclear reaction would just keep right on going.
And this specific design flaw creates an incredibly dangerous characteristic known as the positive void coefficient. You see, liquid water naturally absorbs a small amount of neutrons. So if the reactor gets too hot and that cooling water boils into steam voids, well, suddenly there's less water available to absorb those neutrons. But remember, that solid graphite is still sitting right there, fully moderating the reaction. The result? As the water boils, neutron absorption drops and you get a rapid, highly dangerous spike in reactor power.
Section 2. The poisoned core, setting the trap.
So, the actual catalyst for this whole disaster was the delayed emergency power experiment. The reactor was left running at half power for way too long, and that allowed some really dangerous byproducts to build up. Specifically, this one, xenon-135. Now, xenon-135 is a radioactive noble gas, but more importantly for our story, it is a massive neutron absorber. It absorbs neutrons at a rate of roughly 10 million barns. Think of it like a giant invisible sponge just soaking up all the free neutrons in the core. This xenon buildup dragged the reactor's power down to a sluggish 30 megawatts, which essentially tricked the operators. They thought the reactor was just malfunctioning and needed to be pushed harder.
Fighting this invisible xenon poisoning, the operators broke protocol, and it led to this catastrophic cascade of fatal human errors. First, the grid operator delayed the test, which is what caused that initial xenon buildup. Then, absolutely determined to run their test anyway, the operators intentionally disabled the emergency core cooling system. And finally, fighting desperately to force that sluggish power back up, they yanked out almost all the control rods, leaving only 6 or 7 in the core. Now, the foundational safety rules of this reactor strictly required a minimum of 30 rods to remain inserted at all times just to maintain control. They bypassed literally every safety measure just to push the power up.
Section 3. The fatal feedback loop, 4 seconds to disaster. So with almost all control rods removed and a core heavily poisoned by xenon, the reactor became critically unstable. Down in the reactor hall, these massive 350-kilogram pressure caps actually started jumping and rattling in their sockets. Let's walk through this runaway sequence. Step 1, the coolant water begins to boil into steam. Step 2, because it's now steam, there's less neutron absorption occurring in the core. Step 3, with more free neutrons bouncing around, the reactor power increases. Step 4, this higher power causes even more coolant to boil. It's that positive void coefficient in full effect, and it sent the reactor spiraling totally out of control.
The speed at which this climax sequence unfolded is just absolutely staggering. At 1:19 a.m., the control rods were raised, and the power became highly unstable. At 1:23:40, finally realizing something was catastrophically wrong, the operators slammed the emergency button to drop all the control rods back in. Just 4 seconds later, power spiked to 120 times the normal operating level. We're talking nearly half a terawatt of thermal power reached in mere seconds. And then, the explosion.
But you've got to ask, why did hitting the emergency shutdown button trigger the final explosion? Well, here is the fatal twist. The RBMK's emergency control rods were actually tipped with 6 inches of solid graphite. And as we've already learned, graphite is a moderator. It doesn't stop the reaction, it accelerates it by slowing down neutrons into the highly reactive fission zone. So when they hit that emergency shutdown, they inadvertently shoved extra moderator right into the center of an already boiling runaway core, accelerating the reaction right before the rods jammed halfway down. The emergency brake literally acted as a gas pedal, sealing the reactor's fate.
Now, it's really vital we clear up a very common myth here. This was not a nuclear explosion like an atomic bomb. Actually, scratch that. It wasn't nuclear at all. It was 2 consecutive physical and chemical events. First, you had an initial massive steam explosion as that tremendous thermal power flashed the water to steam, blowing that 1,000-ton lid right off the reactor. Second, this was followed just seconds later by a massive hydrogen explosion, which was caused by the rapid chemical reaction of superheated reactor materials, like zirconium, reacting with the remaining water.
Section 4. The invisible threat. The radioactive fallout.
So, a graphite fire broke out in the exposed core, sending this huge radioactive cloud into the atmosphere. Let's look at what was actually in that smoke. 100% of the reactor's xenon inventory was released, but being a noble gas, it mostly just floats away. The severe biological dangers, those were iodine-131 and cesium-137. About 50% of the iodine was released. It's highly volatile and deposits on anything with surface area, like grass, which contaminated the local milk supply and directly threatened the human thyroid gland. Additionally, about 30% of the cesium-137 was released. This isotope is incredibly hazardous because it chemically mimics salts in our bodies and has a long 30-year half-life. This brings us to a really fascinating question about how radiation actually interacts with biology. When isotopes like cesium-137 get inside the human body, they emit both beta and gamma radiation. So, which type of radiation is actually more dangerous to biological organisms? Take a second and really think about that.
You'd probably naturally assume gamma, right? But internally, beta radiation is the real killer. You see, gamma rays have very low mass attenuation in water, meaning they often pass straight through the human body and out the other side without depositing all their energy. But beta particles, they have an incredibly short range. They stop completely in water and tissue. This means if you ingest a beta emitter, like cesium or iodine, it drops 100% of its energy directly into your surrounding cells, causing massive, devastating, and highly localized damage to your DNA.
Section 5. Measuring the damage. The biology of radiation dose.
Now, you're going to often encounter 2 main units in this field. The gray represents the physical hit. It's purely a physical measurement, the joules of energy absorbed per kilogram of mass. But the sievert, that represents the actual biological damage. It takes that gray measurement and multiplies it by specific quality factors based on the type of tissue hit and the type of radiation. Because, as we just saw, 1 gray of alpha or beta particles absorbed internally does vastly more biological damage than 1 gray of gamma rays just passing through you.
And the type of tissue matters immensely here. Radiation causes the absolute most risk to cells while they're actively dividing. Every time a cell divides, it copies its DNA, and if that DNA was damaged by radiation, that mutation gets replicated, potentially leading to cancer. So, the most susceptible tissues in your entire body are the ones constantly regenerating, the ones packed with stem cells. We're talking your lungs, your stomach lining, your intestinal villi, the thyroid, and your skin.
At severe, acute doses, like an exposure of 4 to 6 gray delivered to the whole body or the gastrointestinal tract, something truly horrific happens. A dose this massive doesn't even give cancer time to form. It immediately kills off your stem cells. Without those rapidly dividing cells to replenish your tissues, your intestinal villi literally die off. You can no longer absorb nutrition, and the body undergoes fatal gastrointestinal starvation. It's a rapid and complete biological system failure.
Which leads us to a final vital point about the aftermath. When looking at long-term cancer risks for much lower doses of radiation, like the fallout cloud that drifted across Europe, the historical data is frankly full of massive error bars. The sample sizes of exposed populations are, thankfully, too low to give us definitive absolute rules about low-dose cancer risks, but half-truths can easily fill that void of data.
So I want to leave you with this final provocative thought to reflect on. With such massive error bars in our low-dose radiation data, where is the exact line between rational caution and media-induced panic? It's an absolutely critical lens to use whenever you're navigating the headlines. Thanks so much for joining me on this explainer, and as always, stay curious.
If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then,